All right, this is the video for section 1.3, the third section of chapter 1. And in this section, we're dealing with numerical summaries of quantitative data. Last section, we looked at taking quantitative data and looking at the different types of graphs we can make. But here now we're going to concentrate on numerical summaries. All right, so we'll look at measures of center, we'll look at measures of spread, and we'll think about which ones are more appropriate for which, which centers and which measures of spread we should use. We'll look at something called the interquartile range times 1.5, or the 1.5 IQR rule, and that will be something that we'll use to determine whether a data value is an outlier in a box plot. Let's see, what else? We're going to look at creating box plots, and then looking at what kinds of graphs and numerical summaries are appropriate so that we can compare distributions of quantitative variables. Okay, let's get started. All right, one of the most common measures of center is the mean. So the mean, or what we would in layman's terms call the average or arithmetic average, is simply the sum of all the observations divided by how many observations there are. So n kind of universally is going to, in this class, going to represent the number of data values in a sample. We haven't really yet talked about the difference between the data from a sample or from a population. So we're going to assume that this is some sort of subset of our population. So small n, the number of data values, and x sub 1, x sub 2, all the way up to x sub n would simply be the individual data values that the variable takes on in all of our data. If you remember from Algebra 2, talk about series, and we use a Greek letter, capital Greek letter sigma, to indicate that we're doing a summation. It's called a summation notation or sigma notation. And so we could take this formula for a mean and condense it down even better and say the sum or sigma of all the x's, and then divide it by n, how many data values there are. All right, and then often we will use as a measure of center the median. So we have mean or the median, and the median is just the middle data value. So it's the value that where half of the data is above it, half the data is below it. And how do we find it? In a distribution, we simply order the data from smallest to largest. It might be just a list. It might be in a stem plot. Some way or another, we have the data arranged in order, and we count up to the middle value. Now, there's a middle value if there's an odd number of data values. Then that means there will be a middle value. If there's an even number of data values, then there is no middle value, and so we take the average or mean of the two most middle or the two center values. We'll go through an example. All right, here we randomly asked 20 New Yorkers, what is your commute time? And in minutes, and they're listed here. So if we wanted to find the mean, well, we would add them all up and divide by 20 because there's 20 of them, and we would get something like 31.25. Now, we're not often going to be asking you to do this by hand. We're often going to put, especially big data sets, we'll put the data in our calculators, and then we'll let the calculator give us our numbers, our number summary for us. We also took that data and put it in the form of a stem plot. Stem plots are in order always. The data is in order, so we can simply count up. And so there's 20 data values, so they're looking for the median. There's not a middle value. There's two middle values, and that is the 0 and the 5, which represents the 20 and 25. So 20 and 25 are the two middlemost values, And so we simply add those up, divided by 2. So the mean of these two middle values, so 22.5 is the median, and 31.25 is the mean. All right, so we're asking this question, what affects the centers? In other words, are they resistant? And when we say resistant, the measure of center is resistant, we're talking about resistant from the influence of extreme values. So let's just think for a minute, this 85, a high end, let's say we turn that, like accidentally that person said 85, but it's really 105 minutes. What would change? Would the mean change or would the median change? Would either of them change? And so I think you can think about, instead of 85 in this list, we're replacing the 85 with 105. So of course the mean will change. The median, however, is resistant to that extreme value. So the median is resistant, the mean is not. So large values will affect the mean. Large values will not affect, or small values, extreme values will not affect the median. All right, one measure of spread is the interquartile range. So it's the range between what we call the quartiles of the data. And we'll see that, we'll get to an example and it'll make more sense, but we calculate the quartiles. So we calculate the, in order to calculate the first and third quartiles, we first have to put the data in order and find the median. And then we look for the median of the bottom half of the data, and that's Q1. And then we look for the median of the top half of the data, and that's Q3. So Q1, we say the first quarter, or Q1 because 1/4 of the data is to the left of it, is below it. And then the third quartile, or Q3, is a data value where 3/4 of the data is below it, 1/4 of the data is above it. And then the interquartile range is simply the difference. So it's like a range. Range is the max minus the min. Here, interquartile range is the larger quartile minus the smaller quartile. So Q3 minus Q1 is the interquartile range. And it is a measure of the spread of the middle half of the data. All right, so let's look at, let's find and interpret the interquartile range for our 20 commute times. First thing we want to do is order the data. And then we want to find the median. And again, this was 20, even number of data, so there is no middle value. If you remember, it's the average of 20 and 25, or the mean of 20 and 25. So 22.5 is the median of our data. Then we want to look for Q3 and Q1 and Q3. We look at the bottom half of the data. Well, there are 10 values in the bottom half of the data. So there are, again, the middle two values, 15 and 15. Clearly, the average of 15 and 15 is 15. And then Q3 is the average of 40 and 70 and 45, so 42.5. All right, the interquartile range is simply the difference of Q3 minus Q1. So we get 27.5. And so how would we interpret that? It just means the range of the middle half of the data of these travel times for New Yorkers in this sample is about 27.5 minutes. All right, now we'll use this IQR as part of our formula to determine whether data should be considered outliers. So before we kind of looked at it and said, yeah, it's outside the range of the other values, it kind of looks like it's going to be an outlier. This is the actual rule for determining whether a data point is an outlier or not. All right, so we take the IQR, we multiply it by 1.5. So 1.5 times the IQR, and then if that value, add it to Q3, if there's any data values beyond that, or any data values below the first quartile minus 1.5 IQR, then those will be considered outliers. Again, an example will make more sense here. So in our example for the New Yorkers, The IQR, if you remember, was 27.5. And then 1.5 times IQR, that would be 41.25. So we add that to Q3. Oh, well, sorry, I'm first going to subtract it from Q1. So Q1 minus that 1.5 IQR. So 15 minus 41.25 gives us negative 26.25. All right, well, clearly there's not going to be any outliers on the low end because no travel time could be negative, right? Travel time to work is 0 if you don't go to work, I guess. But it could certainly not ever be negative. So there will definitely not be any outliers on the low end. And then on the high end, we take Q3, which was that 42.5, and we add to it 1.5 IQR, and we get 83.75. So ultimately, any travel time shorter than negative 26.25, which of course is impossible in this case, or longer than 83.75 would be considered outliers. If we go back and look at our data again, remember 85 was one of our data values. It was the largest. It appears that it would definitely be an outlier. It is beyond or bigger than 83.75. All right, we look at these different values that we've been talking about, Q1, Q3, the median, together with median and minimum and maximum, and we call those 5 things. We use them so often that we call them the 5-number summary, and we're going to use those to help us create a box plot as well. All right, so how do we create a box plot? Again, we'll go through an example which would make this more clear. There's going to be a central box in the box plot, which starts at Q1 and ends at Q3, and then we draw a vertical line through the middle of that segment, through the middle of that box, and that will indicate the median. And then we have little lines that we sometimes refer to as whiskers that come out from the side of the box out to the smallest and largest observations that themselves are not outliers. So we never draw the whisker out to an outlier. Again, it'll make more sense when we go through an example. The outlier itself is indicated by an asterisk or a dot, some sort. Okay, let's look at our travel time example. All right, so here are the travel times. First thing you want to do is, of course, put them in order, and then find our 5-number summary. All right, so we got to make sure that we put a scale on our axis. We're going to put a box plot right above this. Typically, the box plot doesn't touch the scale, but it's kind of floating above it. Okay, so we want to find our 5-number summary. We already saw this data before, so the median, Q1, Q3. And we create this box starting at Q1, ending at Q3, and right through not the middle, but right where the median is, we draw a vertical line. Right? So that indicates sort of it represents the interquartile range there, the data in the middle. And then we take a whisker out to the minimum value. And in this case, we don't take it out to the maximum because the maximum is an outlier. So we take that whisker out to the next biggest value, which is 65. 65 is not an outlier. So the whisker goes out to the largest non-outlier data value. Now we don't consider 65 the maximum. 85 is still the maximum, but in this case, the box plot it just has a dot indicating that the maximum is an outlier. So we don't somehow rework the problem and throw out 85. Sometimes people look at, oh, it's an outlier. We have to get rid of that data value. That is not the case. Just because something's an outlier does not mean we are eliminating it from the data set. So it's still there. 85 is still the maximum. The whisker just does not go out to the maximum in this case. Now, also, sometimes the box plot looks just like that. Sometimes the ends of the whiskers also have a little vertical line similar to the line that indicates where the median is. Kind of your choice how you want to do that. All right, so let's talk about the standard deviation. Standard deviation, another measure of spread. interquartile range is a measure of spread, so is standard deviation. All right, so the standard deviation is just your typical deviation, how much a particular value differs from the mean. So let's look, we asked 9 children, we randomly selected 9 children and asked them, how many pets do you own? So one child said 1, one child said 3, 3 children said 4, one child said 5, one said 7, one said 8, and one said 9. All right, so let's look at calculating. In order to calculate the standard deviation, the first thing we want to do is calculate the mean. So we add up those values, 1 plus 3 plus 4 plus 4 plus 4 plus 5 plus 7 plus 8 plus 9, and then divide those by the 9 children. And then what we do is we calculate the deviation for each value, each observation, each data value. We subtract it. We subtract the observation value minus the mean, and that gives us our deviation. Okay, so we'll have 9 different deviations. So the mean is 5, and so if we look at the observation of 1 pet, that would be 1 minus 4. So this observation here has a deviation of minus 1, and then this observation 8, for example, has a deviation of 3. So one's positive, one's negative. It indicates what direction they're going in. All right, so if we took all of those deviations and added them up, the sum would be 0. You see here it would be 0. So it's not a great, adding up the deviations to see what the standard deviation is isn't going to help us, right? We can't now take that and divide it. It's always going to be 0. The sum of all the deviations will always be 0. So what we do in this calculation is we square all of the deviations. Now they're all positive. And when we add them up, so if they're big, they get really big because they're squaring them. So the sum of all the deviations is 52. We then take and divide that like we're going to do the average, right? We're looking for the typical or average deviation. So we take all those deviations, and it's complicated for y, but this is a sample, and because of something called degrees of freedom, in samples we don't divide by n, we divide by n minus 1. So when we do that, we get something called the variance. And then finally, the last thing we do is we take the square root of that variance, and that's what we get. It's how we get the standard deviation. So in this example, we add up all the deviations. We divide that by n minus 1. So 52 divided by 8, that's 6.5. This value, 6.5, is what we refer to as the variance. Variance itself is a measure of spread, but we take then the square root of the variance, and that gives us our standard deviation. So in this case, the square root of 6.5 is about 2.55. All right, so how do we interpret that? Standard deviation is the average, or what we sometimes say the typical deviation from the mean. So how many pets the kids have, right? Each of the children is going to deviate from our mean of 5 by about 2.55. All right, and then again, if we take the average square of the distances or the deviations, that's called the variance. And then we take that variance, we take the square root of it, and it becomes the standard deviation. So the formula, if we see here, you take x, the observation, x of 1 minus the x bar, that's the deviation for observation 1, we square it, we add it to the deviation for observation 2, and we continue till we get all the deviations squared, added all those up, and we divide it by n minus 1. That's the variance. It's really the square of the standard deviation. So we use it as a symbol for variance, s squared. We use s for standard deviation, as you see up here. S, that is the standard deviation. So s squared is the variance. All right, again, we can use the sigma notation to talk about adding them up instead of writing all this out every time. we can simply use the sigma notation to indicate that we're adding all those up. And then again, the standard deviation, we denote that with an S and from a sample, and that is just the square root of the variance. Now, often we're not going to have to calculate the variance by hand or the standard deviation by hand. It's a tedious process if the data set is large. We will typically put those data values into our calculator and have it calculate them for us. I believe there's probably one homework problem that is a simple set of data values that's asking you to calculate it by hand. I will show you in an example in a later slide how to calculate on your calculator the standard deviation. All right, so certain measures of centers go with certain measures of spread. So if you were talking about the mean for the center, then you really have to talk about the standard deviation as the measure of spread. Those two go together. It'll make more sense when we get to later chapters. Median, if you use the median, then you typically use the interquartile range or just the range. The range just being the maximum value minus the minimum value. All right, which measure of center should we use? And so the median and the resulting interquartile range or range are better when we have skewed distributions. So remember that the median is resistant to extreme values. So skewed distributions, we should be using the median. And if we're using the median, we should use interquartile range or simply the range. If we use the mean, then we should be using standard deviation, but we do that for symmetrical data that don't seem to have any outliers. They're fairly symmetrical. All right, so a number summary, like we've been talking about in this section, is great, but you really should plot the data. It helps us really see whether the data is symmetrical or whether it's skewed, and that will help us determine what type of measure of center and resulting spread we should be using. All right, when we organize these statistical problems, we're going to start using a four-step process. In a couple of chapters, we'll switch over to a three-stepper, but when we get to the last chapters of the book, when we're doing inference, we'll definitely go back to these 4 steps. So 4 steps, it's how to organize these sort of rather long problems. These problems can take a half a page, sometimes even a whole page as we get to later chapters. So you really should start using these 4 steps, and there is one problem in homework tonight that requires it. So the first step is the state. You basically are restating the question that you're trying to answer. Plan, you're going to talk about how, what process you're going to use to try to answer the problem. So what statistic techniques are you going to use to try to solve that problem? And then you're going to actually do the calculations, make the graphs, whatever it is that you said you were going to do in the plan, you're actually going to do it in the do. And then you're going to sort of wrap it up. You're going to give a conclusion based on what you saw in the do. So you're going to answer the question in the context of the real world problem. All right, so this is your homework for section 1.3. And just remember that some of the problems are going to be a 4-stepper, and actually 105 this time is. And when you look at the book, you can tell which ones are 4-steppers because they have this little symbol here that looks like a staircase, and it says 4 steps. Now later on, they'll stop giving us those symbols because you'll need to just know, but that's for later chapters. For now, if it's 4 steps, they will tell us. So remember, when you're doing this homework, you make sure that for 105, you're using your 4-step problem. So use your state, use your plan, use your do, and use your conclude. We'll go over that when we discuss this homework next class. Meanwhile, we're going to continue with some of the problems on the notes. The notes continue on page 4 and 5, and the following will take you through some examples on how to use your calculators. All right, I'm now going to kind of show you a couple of things that you can do in your calculators. Now I'm going to kind of go through this quickly. You should pause the video in order to put the data into your calculators and whatnot. But pause the video whenever you need. But for the sake of time, I'm just going to kind of walk through these last 2 pages of your notes. So the first thing we're doing is we're just going to look at using our TI-84 to do a couple things. So we have the set of data we asked. I think it's 15 males. How many text messages did you send in the last 24 hours? And this is the data. And so we want to put this data into our calculators. So you want to hit the button Stat and Edit, and that takes us to a screen that has a bunch of lists in it. Now, depending on who used this calculator before you, you may have data in lists. So like here's some data in a list, has nothing to do with our data. It's old data from an old example. We want to clear it out. All right, so if there's any current data in there, then you really want to do is you want to hit the cursor up button on your calculator, and this is going to take us up, and you want to highlight the actual name of the list. So you want to highlight list 1. You then hit the clear button and then enter, and then it erases the entire list. And it doesn't delete the list. L1 is still there. Its content has been erased. So you don't want to hit, while the L1 is highlighted, do not hit the delete button. It actually gets rid of the entire list for you, and you don't want to do that. You want list 1 there. You just want it empty. So you highlight list 1, go up, highlight list 1, and then hit clear, and then enter, and then your list should be empty. At which point now you go and you type in all the data values. So you type 127, hit enter, type 44, hit enter. So type all those in, pause this if you need to. Once you get all that data in, notice that once you're finished with the last 15th data value, you hit enter, the calculator is now asking you for the 16th data value. So you know you're done because it's asking for an entry value 16, where we have entered 15. So we know we're done. And so now you want to do a number summary. So you want to hit the stat button again. Again, pause if you're still putting in data. So hit the stat button and then hit cursor over to calculate. So you can see that edit is the option that comes up. Cursor over to calculate. The first option is a 1 var stat. So you can either hit a 1 on your calculator or hit enter because 1 is highlighted. And so that is telling us we want to do a 1 var stat. That's going to look at one variable, in this case the number of text messages sent, and it's going to give us a number summary. So the frequency list you want to leave blank, and then cursor down to calculate and hit enter, and then you end up getting something that looks like this. The first value here is X bar. That's the mean. So the mean of our data should be 62.4. If you didn't get that value, double check that you didn't enter some of your data wrong. And then it also gives us S sub X. That, what we just talked about, is the standard deviation. So it gives us values. If you cursor down, it will also demonstrate to you all the 5-number summaries. So cursor down and it will give you how many data values there were. It'll give you the min, give you Q1, the median, Q3, and then the max. And you can cursor kind of up and down. So this gives us the entire number summary, everything we want to know about this data list. All right, let's look at how we would create a histogram with this data. So the same data in your calculator, you want to go and hit second, the blue button at top left corner. So second, and then y equals, and this takes you to your plots. Now, depending on your calculator, if all of them say off, you're good and you don't have to do this. But if any of them say on, then you should just hit the 4 button. And that selects that you're going to turn them all off. So that automatically turns everything off in case you have a couple things on or off or whatever, in case you've used this calculator in another class. it now turns off all of your plots. Now go back, do the same thing, second y equals, and let's go into plot 1. So either hit a 1 or hit enter. And so now you're on this screen. You want to turn the on, so go highlight the on, cursor down, hit on and hit enter. That turns it on. And then go cursor down, and you want a cursor over. You want this little graph here that looks like a histogram. You might have to cursor left and right to get through these, depending on where you are, but you want to highlight it and hit, enter, and it now makes it dark. So you're in histogram mode. And then it asks for what list is your data in, so probably list 1. If it's not, go down and change that to list 1. Go down to your X list and hit second 1, and it will put L1 in there. Frequency, leave it alone for now. We want that to be a 1. All right, so now we hit graph, and you'll probably see that nothing happens because your window on your calculator is set up to show a certain range of your XY coordinate system, and your graph is not in that. And so as a result, you're not going to probably see anything when you hit graph. And so as a result, you should hit your zoom button. So hit zoom, which is the top center button of your calculator. And then we want to do zoom cursor down to zoom 9, or just hit 9. And so that's called zoom stat. And what that does is it zooms in on your particular, the window necessary to show your data properly. So you notice here we have a histogram clearly skewed to the right. All right, now what could we do to create a box plot instead? Again, same data, we're not going to change that. We want to go back to second y equals, go to plots, go back into plot 1. This time we want this little guy here. Both of these look like box plots, but we never really want to use this one. We want to use this one. It's got little outliers. So it doesn't mean you're going to get outliers, but if there are outliers, they'll show up. This one is not a modified box plot. We want a modified one, which will always demonstrate to us outliers if they're there. Okay, so list 1, frequency, we want to leave that alone at 1. The X list is list 1. And then this mark tells us what the outliers are going to be displayed as if there are outliers. This will be what we use to display them in our graph. And so you hit graph, and you, again, might have to hit zoom 9, but you should get a graph like this. Okay, and then the last thing we want to do here is show you how you could do 2 at the same time. So now what we want to do is go turn on plot 2. So go back to second y equals, and cursor down to 2, and select that, and also turn that one on. Okay, and now we want to go back and change that one also to a box plot and make it list 2. All right, after you put this data in, of course. So put the female data into list 2, and then go and turn this plot on. Okay, you'll get an error if you try to plot using data that's not there. So you first want to put this data in and then go do this. And then you can get a side-by-side box plot. Again, you might have to do a zoom 9 in order to get it to work properly, depending on the data. So this data goes out further, so you'll have to hit a zoom 9 to get it to resize the scale so that these bigger values show up. All right, so let's talk about some different ways that you can enter data. Again, I'm just going to talk through this, pause the video to get your data in. So here's some raw data. Don't even know what it was. I just made this data up. But you can see it's 0, 0, 1, 1, 1, 1, 2, 2, 2, 2, and so on. And so if we wanted to make a histogram with this, we would simply go up to list 1, clear out that list, right, because we have some data in there, clear out list 1, even clear out list 2. So go up, highlight L1, hit clear, enter, and do the same thing for L2, all right? And then go type all this data in. Once you get that data in, we can go second, y equals again, go into the plot one, and make it look like a histogram. Also, make sure you might want to just turn off the other plot. So turn off plot 2. Again, remember you can hit 4 when you hit second y equals. You can hit 4 to turn off all the plots, but you can't have 2 histograms on at the same time. It just doesn't work. But you can have 2 box plots, which is what we just did. All right, so what we want is a histogram, list 1, leave frequency alone. This is what the newer calculators look like. All 6 are on one line. The older 84s have those graphs on 2 lines. So, you know, some of my graphics use the newer system, some of them use the older system. All right, and then hit graph, and you will probably have to hit zoom 9, zoom stat, to get the data to show up. Okay, and so that's a histogram. All right, and then let's talk about different ways of entering some of this data. So you probably noticed it was kind of annoying to type 2, enter 2, enter 2, enter 2, enter. To enter this data up here was kind of annoying. Instead, what we could do is give you the data in a frequency table. So instead of listing 0, 0, listing it twice, I can use a frequency table and say 0 and saying how many there are. There's 2 of them. 1, and there's 4 of them. 2, and there's 5 of them, and so on. So this is the same set of data. The top one is just raw data. The bottom one is using a frequency table. All right, so let's say, how would we enter this data using a frequency table? So first, go clear out list 1. All right, so clear out list 1. And then what you want to do is put the X values. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Put that in list 1. And then in list 2, you're putting how many of those numbers. So next to the 0, you put a 2. Next to the 1, you put a 4. Next to the 2, you put a 5, and so on. So the frequency data is in list 2. Okay, and there are, what, 11 data values? Yeah, 0 to 10. There's 11 different types of numbers, and so the frequencies just go next to them. Okay, it's really important that those line up. If you skip a number accidentally, it'll screw things up. So make sure that those line up according to how they are vertically in the table. All right, so then we want to go hit second y equals, turn on plot 1. If you have any other plots on, turn them off. So plot 1. So this time we want to leave it as a histogram, and list 1 is the X list. The frequency is list 2. So you get to that by hitting second and then 2, and it replaces the 1 that's there. So go highlight the 1, hit second, and then 2, and that gives us list 2. All right, then that would give us this graph. So the graph looks the same. You really wouldn't know that you entered the data any differently. You have the same histogram in either case. But sometimes if you have large raw data sets, it's just easier to have the data given to you in a frequency table. All right, so now notice too that the histogram that they gave us has how many classes, how many bars does it have? 1, 2, 3, 4, 5, 6, 7. That doesn't really jive with our table. Our table has sort of 11 different data values. And so if we hit the trace button on our calculator, that is, let's see, where is trace? Trace is the top, sort of top right corner. The second from the top right corner is trace. So if you hit that, it highlights one of the tops of one of the bars, and it tells us the class width. Class width is from 0 up to 1.6 repeating, which is kind of a weird class. The calculator takes the data and divides it into 7 classes by default. And sometimes that doesn't really go along with our data very well. It also tells us next to that how many observations are in that bar. So it tells you the height of that bar being 6. All right, well, that's not really great. What we want to do is we want to change the class width. And we can do that in our calculators. So we hit the window button, which is the second from the left at the top, window, and it gives you this here. And you want to change this. You want to change the X minimum. So think about it. What do we want? We really want the left-hand value to be 0 and the right-hand value to be 11. Yeah, I know the top value is 10, but remember, the bar always goes to the right of the data value. So 10 is displayed in the bar between 10 and 11. So we want the maximum X value to be actually 11. Okay. The X and Y scale is just enough so that we can see the big values. So like 6 is the highest frequency. So we just want to make sure that our maximum Y value is above 6, or we wouldn't be able to see the top of this bar. I went up to 10, plenty of space. Sometimes I go a little bit below. I went -3 just so we had some value, some space down below. These purple numbers actually you'll notice, don't show up when you go to graph this. This is just showing you that it's from 0, 1, 2, 3, all the way up to 11, and that's why we needed this 11 here. All right, so once you hit those, you just hit graph. Now, don't hit zoom 9. Zoom 9 will take us back to the graph we just had with 7 classes, which we don't want. We want these 11 classes that we have. All right, and then once you hit graph, you can again hit the trace button, and you can see the first class is from 0 up to, but not including 1. Now this data is all integers, so it's nicer plugging it in. But these classes make more sense with the data that we have. Okay, and it also tells you that there were 2, so that corresponds to the frequency 2 here down below.